We're going to talk a little bit about linear programming problems. And so linear programming problems, sometimes one of the trickiest things about them is just realizing whether you're dealing with them or not, and especially when we've got all sorts of other types of word problems in this chapter. Linear programming is all about optimization. You're trying to optimize something, which means maximize or minimize something. And so that's sort of a key word that you're going to be looking for in these problems is, am I trying to maximize or minimize something? And so this problem's got a whole lot going on. We can read through it. We're shipping bottled water and medical supplies to survivors of an earthquake by plane. Each of those things helps different numbers of people. So bottled water will help 10 people, medical kits will aid 6 people. And we're limited by a couple things. We're limited by the pounds on the plane and by the cubic feet on the plane. And so we have to sort of fill up the plane in the most efficient way to help the most people. And so in general, when we're working on these problems, the first step is going to be to define your variables. As it says in this screen here, this can be a little bit tricky. You want to think about what decision you're making in this problem. And so in this problem, sometimes people think, oh, the variable is pounds or people or so on. You want to think about what's the question. That's in the last sentence. Determine how many bottles of water and how many medical kits you will be shipping in order to maximize the number of people helped. And so when we set up this problem, I would encourage you to actually write down what your variables are. And so I'm going to do x to be, where's my writing here? I'm going to do x to be the number of bottles and y to be the number of medical kits. Okay, and so you want to make sure it's real clear what you're deciding. That's going to drive your variables. The next step is going to be to think about the constraints, what's holding you back. And so those are typically going to be inequalities, and so you're going to write an inequality for each constraint. So I'm going to have you think about this in your groups. And so we're going to have two constraints. We already talked about them a little bit. We're going to have one based on volume or cubic feet. Well, I guess that's the second one in the problem, but that's fine. Volume or cubic feet. And then the other one is weight or pounds. So take just a second and pause the video and then talk about it in your groups. What would the two inequalities be to make sure we have the appropriate volume and the appropriate weight? So pause the video, and then when the groups are ready, you can continue. All right, welcome back. So now we're going to look at the volume. We'll wait for the announcement here.
Fletcher Gornick, can you please come to the main office? Fletcher Gornick to the main office.
So if we think about the volume, we're going to write an inequality for the volume. And we know that the volume cannot be more than 6,000 cubic feet of total supplies. And so we know we have to keep that volume less than or equal to 6,000 cubic feet. And so where does this come from? Well, the volume comes from, let's see down here, 1 cubic foot per water bottle and 1 cubic foot per medical kit. And so since they're both 1 cubic foot, that's pretty easy. We just have 1x plus 1y has to be less than or equal to 6,000, right? 1x, 1y has to be less than or equal to 6,000. What about the weight? The weight, we have a maximum of 80,000 pounds, and the bottled water weighs 20 pounds and the medical kit 10. And so we want to keep the total weight less than 80,000 pounds. So less than or equal to 80,000 pounds. And it was 20 for the X for the bottles of water and 10 for the medical kits. So hopefully you guys had something along those lines in your group. So we have our variables that we're trying to decide. These are the constraints that are holding us back. And if it's not a bad idea just to remind ourselves, of course, you can't send negative amounts of anything. And so we're going to also have constraints telling me that these things have to be at least 0. Okay. So our next step is going to be to graph each constraint, and we're going to see the region where the constraints overlap. So take a minute to do that in your groups again. So we're looking at these inequalities. We're basically just looking at the first quadrant because x and y are positive. Just sort of sketch out the graph of each of these inequalities. And again, we'll pause the video and then come back when you're ready. Okay, welcome back. And so now we're just going to sketch the first quadrant, and I'm just going to sort of rough this in, get a reasonably accurate graph. And so I usually do these by the intercept method. And so we're going to have, for this first inequality, if I cover up the x, if x is 0, the y-intercept is going to be 6,000. And if I cover up the y, the x-intercept is also going to be 6,000. And so you sort of have to decide a little bit on what your, scale is going to be on your axes. Maybe we'll go with 500 for each one. So every 2 boxes is 1,000. So 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. So that's the x-intercept for that first one. And the y-intercept would again be 6,000, 1, 2, 3, 4, 5, 6. And it can be equal to 6,000, and so I'm going to have a solid line, and I'll connect these up with a solid line. And I want it to be less than or equal to 6,000, and so I'm going to be sort of on the inside of this line, and maybe just make a little note by putting some arrows there. Okay. For the next one, the next constraint, we have 20x. Sorry, I don't know why that is bouncing around. Let me try to get back here. It's still there. I don't want that. Sorry about this. I'm just going to try to start over. And so I'm going to graph that second inequality. And so if I cover up the 20x, when I divide 80,000 by 10, I'm going to get 8,000 for the y-intercept. So 7, 8. So there's 8,000 for the y-intercept. And when I cover up y, 80,000 divided by 20 is 4,000. And so that is the x-intercept. And so again, I'm staying in the first quadrant. If I had a ruler, you know, I could connect these pretty nicely with the ruler. I'm going to be inside that one also because I need to keep that weight less than 80,000. And so I'm looking to see, when I look at my steps here, I'm looking to see what, where the constraints overlap. And in particular, I'm interested in those corner points of the region, the corner points of the region. And so I've got this region inside here, this sort of quadrilateral. And I see it sort of has 4 corner points. Of course, I have 0, 0 down here in this corner. I have 4, 0, and of course that's really 4,000, 0. I was counting by thousands. Up here I have 0, 6,000. And I now need to find the intersection of these two lines. So it's just a little system of equations. I just need to know where these two constraint equations were crossing. So I have x plus y equals 6,000, and 20x plus 10y equals 80,000. And of course, I can sort of see where they're crossing on my graph. My graph looks pretty neat, if I do say so myself. And so hopefully this intersection graphically is accurate, but I want to verify it algebraically. I'll do this by elimination. I'll multiply the top equation by negative 10. So I get negative 10x plus negative 10y equals negative 60,000. And then the second equation is 20x plus 10y equals 80,000. I add them together. I get 10x equals 20,000. And sure enough, when I divide by 10, I get x equals 2,000, which looks good based on my graph here, so 2,000. And then if x plus y has to equal 6,000, if x is 2,000, then y is 4,000. And so I now have my sort of region of possibilities. So anything that I want to put on that plane has to fit into this little corner region. And it's going to turn out as maybe not a huge surprise. We can talk more about it at the end of the week if you want to see why this is. But it turns out that the best possibility is always going to be one of the corner points. Because basically, if you're not at one of the corner points, you can sort of move out a little bit farther, get a little bit more on the plane, and help even more people. And so the final step is picking the corner point that helps the most people. And so to do that, we have to think about, well, how many people are we helping, right? How many people are we helping? And so when we go back to the problem, that's up here at the second sentence. The bottled water helps 10 people, and the medical kit helps 6 people. And so take a minute again in your groups, try and write the objective equation. So number of people helped. So take a minute in your groups, pause the video, see if you can write the equation for the number of people helped. Okay, welcome back. And so we remember that the two key numbers are 10 and 6. And so we have 10 people helped by each X, 6 people helped by each Y, and you can just call that capital P or something for the number of people helped. And so we basically want to know which of these 4 corner points, we can sort of eliminate the 0, 0 right away, is going to help the most people. And so we're just going to list the point and then the people, and we're just going to list them. 0, 0 would help nobody, right? We didn't send anything. What about 0, 6,000? Well, 0, 6,000, 0 helps 0 people. 6,000 times 6 is 36,000 people. So if we filled up the plane with medical kits, we'd help 36,000 people. If we filled up the plane with water bottles, we would help 4,000 times 10. We would help 40,000 people. And the last one is sum of each, 2,000 and 4,000. And once we've done that, we're going to have helped 20,000 people with the water and 24,000 people with the medical kits. And so 20 plus 24 is 44,000. And so now we simply pick the one of these that is the best. And so this is the last one in this case. So we would then write out the answer, making sure it's clear what's what. So we would use 20,000 bottles of water, 4,000 medical kits, and we would have helped 44,000 people. So I think this has hopefully been review from Algebra 2. We will have these steps posted on the student resource document, so you can always check that out. And on the student resource document, there are also some additional resources about solving linear inequalities and some linear programming resources. Thanks for listening. Have a good rest of the day.